Well, hello everyone. In this video, I wanted to make a continuation of the previous video that I uploaded, in which I start talking a little bit about what are the generalized Morse wavelets. In this second video, I want to deepen the discussion into what are actually the generalized Morse wavelets, and that is basically section B of the paper titled Applications of the Generalized Morse Wavelets, a Review. And before I start talking about the generalized Morse wavelets, I also wanted to well, make a recognition of the work in which the generalized Morse wavelets were first not introduced, no, but were explained in a systematic way. And that is the work of reference 1821 and 30. That is the work of Lilly and Olhidi that was published in 2012 in the IEEE Transactions on Signal Processing. Um, Also, we have this other reference that is the work also of Olhidi and Walden that was published back in 2002, also in the IEEE Transactions on Signal Processing, where the generalized Morse wavelets were first introduced in a systematic way, I would say. And also we have this other work that is on the analytical wavelet transform, also published by Lilly and Olhidi back in 2010. And this was published in IEEE Transactions on Information Theory. And I am citing these works because basically what I did in this work was to summarize the applications and the theory of the generalized Morse wavelets. But in fact, their work was a basis to develop this article. And well, now, focusing on what are the generalized Morse wavelets, well, basically we have the following representation in the frequency domain, in which we have the frequency domain representation of the generalized Morse wavelets. Um, Basically, this expression defining the frequency domain represents an analytical function. We know that because you can see here that we have a unit step defined in the frequency domain. This means that these wavelet functions are only supported for the positive frequencies, which makes these functions analytical. A is basically a normalization constant of the wavelet basis function. But the important fact here is these two parameters, beta and gamma. Beta basically allow us to control the form of the wavelet in the time domain, and gamma allow us to um, control the function in the frequency domain. So beta helps you to control how the function behaves in the time domain, and gamma helps us to control the way the function behaves in the frequency domain. So we have this general expression, and we call them generalized Morse wavelets because by only modifying these two parameters, we can get a whole family or many type of wavelets that are already available in the literature, like the Airy wavelets, the Shannon wavelets, the Beazley wavelets, or the derivative of Gaussian wavelets. No, and in the derivative of Gaussian family, we have, for example, the Mexican hat wavelet. No? So we have a bunch of wavelet types that can be derived from this expression, no? Or from this representation. And also, another way in which we can characterize the generalized Morse wavelets is by using a metric that is called the Heisenberg area. The Heisenberg area can be computed by considering the standard deviation of the function in the time and frequency domain. Now we are basically multiplying the dispersion of the two of the same function, but in the different variables, the time and the frequency domain. And basically, this Heisenberg area is basically a metric that tells us about what is the degree of energy concentration of the function in both domains. The better, well, the lower, the better, no? Also, we know, according to the Heisenberg uncertainty principle, that this Heisenberg area has a lower bound of 1/2 or 0.5. That means that no matter which function we use or we analyze to perform wavelet decomposition, we have this theoretical lower bound established by the Heisenberg uncertainty principle And that is basically how much energy we can concentrate of the function in both domains simultaneously. But in the case of the generalized Morse wavelet, we will see later that we can approximate this lower bound when we set the value of gamma equals to 3. Before deepening into that aspect, I wanted to show you this graph that is also based on the work, on reference 18 of this work, that as you remember, it is the work of Lillian Alhidi. I basically took the package that they developed to plot the generalized Morse wavelets to generate this graph. So these are correctly referenced in this image and also along the paper. But the reason of showing to people this graph is that you can see how if we fix, for example, um, gamma and we increase the value of beta, we are basically changing the number of oscillations of the wavelet function. No? Depending on the value of the setting between gamma and beta, have different behaviors in the time domain representation of the function. Also, in this other graph, this is the time domain visualization of the wavelets for different pair values of beta and gamma. And this is the frequency domain representation of the same wavelet or the same parametrization. Here it is, here you can see that depending on the value of gamma, you will have a very skew behavior in the frequency domain representation of the wavelet. But you can appreciate that when gamma equals 3, we are having a more symmetric behavior. No, it behaves like a normal distribution. Now, if you have some statistical background, you will see that these bandpass filters, because in fact these wavelet functions behave very similar to bandpass filters, um, will have a more symmetric distribution in the frequency domain. And that is helpful because we can be certain that we are centering the central frequency of the wavelet in a certain region, and that the dispersion in the left and the right side will be the same. No? So to some extent, we are having a better precision. Also, you can also see that as we fix the value of gamma and we increase the value of beta, we are having a much narrower behavior in the frequency domain. Okay, so we're increasing the precision in the frequency domain, but at the same time, you can see that we're increasing the dispersion in the time domain. No? And this is related to this trade-off of the Heisenberg uncertainty principle that, okay, you are having um, better um, frequency resolution, but at the expense of a lower time resolution. But at the same time, you can see that when we are having a very straight a narrow representation in the time domain in this region, you are having a wider, no, precision, no, or a higher standard deviation in the frequency domain. No, so there is also this trade-off of these gamma and beta values when we are working with these generalized Morse wavelets. And this is interesting because we can see from this graph that these generalized Morse wavelets are not contradicting the Heisenberg uncertainty principle. No? And this is basically a statement. No, if you read this part of the paper, I don't want to depend too much in the theoretical aspect, but we are basically explaining here um, which type of functions allow us to approximate the lower bounds of the Heisenberg area. And this is other way in which we can parametrize the generalized Morse wavelets. We can get what we call the time bandwidth product that is defined as P, that is equal to the square root of beta times gamma. So this is another letter in which that we can use, or another relationship that we can produced to parametrize or to define the generalized Morse wavelets in this form. And what else? Well, in this section, uh, what I basically, what we're basically expressing is that we are changing the value of gamma and beta, and we are plotting or representing through this color scale how the Heisenberg area is changing. So you can see that the darker tones represent a lower Heisenberg area. In fact, the darker the tones of colors that we're showing here, the more proximate we are to the Heisenberg area lower bound. That is very near 0.5, no, according to this color scale of this plot. But one of the things that I wanted to highlight is that when you define gamma equals 3, you're basically approximating this Heisenberg area lower bound. No? Here in this region, we will obtain a Heisenberg area that is very close to 1 over 2. So this is a property or an advantage of defining gamma equals 3. But one of the problems that we can see and by defining gamma equals 3 is that we are also increasing the value. Well, there is a whole range, or maybe we can say there is an infinite range of values that beta can take within this region. So one question that remains to be answered is how should we define the value of beta? No? What is the most appropriate way in which we can define this value of beta when we fix gamma equals 3? Because we know that in this region we can approximate the Heisenberg area lower bound, but also at the same time we can see that the value of beta is can be set arbitrarily, no? Because there is a lot of values that we can take with this is very specific region or this Heisenberg area space, no? And but also you may remember that there is also a trade-off. Maybe we can select a very high value of beta in order to define this Heisenberg area, this parametrization of the generalized Morse wavelets, but also we are affecting at the same time the resolution that we can get in the time and frequency domains, no? By setting the generalized Morse wavelets uh, for a particular value of beta, no? There is a trade-off between these two. Well, by setting the value of this parameter, either it is a low value or it is a high value. So the question that remains, and that we also wanted to highlight from this review, is how should we parameterize this value of beta? No, there is an open question there. No, which methodology or which criteria we can use in order to try to set the value of beta? No, what is the best value of beta according to the type of system or process or data that I am analyzing? No, how should we get that? No, so there is an open question on future work that we try to address in another publication. I will be explaining that in another video. But the aspect that I wanted to highlight is that despite that we have this superfamily of the generalized Morse wavelets, its parameterization is challenging. No? In fact, I will be uploading a second video discussing what those people do, no? How do people parametrize this superfamily of wavelets, no? If any of those publications there is a justification to that. So I think that I will be ending this second part of this video discussing the applications of the generalized Morse wavelets, no? That remember that it's a review paper that I published a couple of years ago. In fact, this was published back in December of 2022. So it has been almost more than 3 years, I will say. But if you want to get into this paper, I will place the reference and the link to this paper in the description of the video. So see you later.